booster ignition, and liftoff of Discovery, hoisting harmony to the heavens and opening new gateways for international science. Discovery has cleared the tower.
How exactly does the nutrient uptake from soil and rock work in different climate zones? A landscape with heavily weathered soils and hardly any pristine rock remaining is covered by a dense forest. There is heavy rainfall, so soil moisture, symbolized by the blue dots, is high. But where do the trees get their nutrients from when there are hardly any of the original rocks left? A fascinating cycle begins. Phosphorus, in red, is an important mineral nutrient found in rock and soil. Phosphorus is largely absorbed by fungal hyphae. These fine white fungal tissues are connected with the roots of many trees. Fungal hyphae help phosphorus get into the roots, from where it migrates to the tree trunk and then to the leaves. But this process costs energy. The leaves absorb carbon through photosynthesis, some of which is delivered back to the roots. There it is partly transferred to the fungal hyphae, which draw energy from it. Additional carbon is also released into the soil, where it accumulates over many years and turns the soil dark brown. The organic carbon accumulates in the soil. In autumn, the leaves fall and decompose into soil organic matter. This makes the soil even darker. In addition, the phosphorus contained in the leaves can be reabsorbed incredibly efficiently by the dense network of fungal hyphae and recycled again through the tree, released as leaf litter and taken up again and again. This is a recycling ecosystem. It draws much more mineral nutrients from the leaf litter than it does from the rock. In a dry area with little soil moisture, this is quite different. The only vegetation is shrubs and cacti that grows slowly and not very densely. Nevertheless, these plants also absorb their nutrients with roots and fungal hyphae. But since little litter is produced each year, not much organic soil material is formed, which would supply fungal hyphae and vegetation with nutrients. This means the fungal hyphae have to find the nutrients deep in the rock. Since there is less vegetation, less carbon is also transferred to roots and fungal hyphae. The entire nutrient cycle is slower, and nutrient fluxes are lower. This ecosystem is acquiring because it draws its mineral nutrients mainly from the rock. In the humid area, here on the left, there are not enough nutrients in the soil. The fast-growing ecosystem is sustained mainly by recycling. In the dry area, here on the right side, with sparse and slowly growing vegetation, the nutrients are mainly supplied by uptake from the rock. This is the fundamental difference between element cycles in ecosystems of different climate zones. So how do we combine all the findings of the landscapes with data of their vegetation? One possibility is by using computer simulations. Tectonic forces push up the surface and lift it to higher and higher elevations. Earth's surface represents a delicate balance between tectonic and climatic forces, which through erosion removes material and lowers the surface. These models are based on what we think are the best mathematical relationships to explain how different processes work on this landscape. For example, hill slope processes convert bedrock into soil, which then moves downslope to rivers. Rivers take this sediment from the hill slopes and flush them downstream if there is enough water. One of the biggest questions facing geoscientists today is how different would this landscape look if vegetation were on it? In this computer model, we can see how the addition of dense vegetation to the Earth's surface would influence the landscape development. To grow dense vegetation, we need large amounts of rainfall. Plants influence how the rivers erode into the landscape and how sediment makes it to the rivers. They intercept rainfall, which limits the water's ability to erode Earth's surface. And because of their protective effect on the mountain slopes, the plants concentrate water runoff and erosion into large, deep valleys. However, as uplift continues, the mountains between the valleys rise higher and higher. If we zoom into one catchment, we see that vegetation obstructs the flow of water and focuses it in channels. We can also see the deep weathering of rock by water and plant roots. This landscape is very similar to what we see in Parque Nacional Nahuelbuta in south-central Chile. This next computer model shows how different the land surface looks with very little precipitation and thus little vegetation on top of it. The sparse vegetation is unable to protect the surface from erosion, so even though there is less rainfall, it is easier for it to erode the hill slopes. Because of the low water flow, only small river valleys form. The eroded sediment is transported into a dense drainage network of many small rivers. Due to a lack of water, a lot of sediment remains in the valleys. Drought and reduced plant cover also lead to less weathering and thinner soils. This example of an arid landscape with very little vegetation is similar to what we see in northern Chile, in the Parque Nacional Pan de Azúcar. Do we now know what happens when life meets rocks? Not quite yet. What our experts say is that although they can quantify dependencies, these dependencies always run in both directions, from life to rocks and from rocks to life. It is based on a fundamental property of coupled natural systems: feedback.